Hello, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. So we have a bunch of questions that I see saved up here. Let me try and take a look at these. Let's see. There was a question here from B2 asking, what is beta decay? Okay, let me see what I can do about that one. So, most of the time when we have atoms, all standard matter is made of atoms. There are the atoms, the different types of atoms are the different entries in the periodic table, hydrogen, helium, lithium, beryllium, boron, and so on. Each of those different entries in the periodic table represents an atom with a different number of protons in its nucleus. So hydrogen has 1 proton, helium has 2 protons, and so on. The nucleus of an atom has both, can have a bunch of protons in it and also has a bunch of neutrons in it. Protons are positively charged, they have electric charge. Neutrons have no electric charge. So most standard kinds of atoms have I'm sorry, my computer is going crazy and overheating itself. I wonder why. Let me see what is happening here. Interesting. Okay, in any case. So the most standard kinds of atoms, once you make that kind of atom, you're stuck with it, so to speak. You make some hydrogen, you make some tungsten, you make some gold. It's just going to stick around forever in that form. Nothing will happen to it. But some kinds of atoms, some chemical elements are unstable, and the nuclei will just self-destruct after some amount of time. And so, for example, if you go beyond uranium, which is element number 92, has 92 protons in its nucleus. If you go beyond uranium to elements like plutonium, actinium, polonium, all these kinds of things, you will those atoms have nuclei that are not stable and will spontaneously self-destruct. And when they self-destruct, they produce, they're said to be radioactive. And the reason they're said to be radioactive is because when they self-destruct, the pieces that come out are radiation. They're going at, they're usually going at high speed, and they're sort of the fragments of that nucleus that break apart and produce radiation. And that radiation can be quite harmful because, the little fragment of some nucleus that breaks apart is going at very high speed, and it's just a little particle, but if it hits a piece of DNA in one of your cells, it can disrupt that DNA, and that can eventually lead the DNA to make that cell become cancerous or whatever else. So it's kind of bad to get radiation from self-destructing atoms to go through you. So in any case, the main so that's sort of the idea of radioactivity, is when there's sort of self-destructing nuclei in atoms. And that's the only way that an atom of something like gold or hydrogen or whatever else ever changes into anything else, is by its nucleus sort of self-destructing, or maybe something kicking its nucleus so hard that it changes or self-destructs. Okay, so when nuclei self-destruct, this was something discovered, the radioactivity was discovered around 120 years ago now. And when it was first discovered, people identified 3 different kinds of radioactivity: alpha decay, beta decay, and gamma decay. It turns out there are actually some additional kinds of radioactivity. A very common one is called spontaneous fission. Spontaneous fission, what happens is it's a big blobulous nucleus, and the thing just doesn't hold itself together quite strongly enough, and eventually it just falls apart. And that's what happens, for example, to uranium-235, which is famous because it's what's used in lots of nuclear reactors and things like that. And it falls apart very slowly. It takes 1 billion years on average, to fall apart. But it falls apart by spontaneous fission. It just sort of is too big a nucleus, and it can't quite keep itself together. The strong nuclear forces can't quite keep it together, and just falls apart. Okay, so there are other kinds of, these kinds of radioactivity, alpha decay, beta decay, gamma decay, they're all different kinds of radioactivity, and they're all really quite different. When they were first discovered, people just said, oh, the nucleus fell apart and it produced radiation, and they were just sort of, they didn't really know that they were so different. But so what are those different kinds of radioactivity? Alpha decay is the nucleus basically falls apart by emitting a piece that is 2 protons and 2 neutrons. It's like the nucleus of helium-4, and that whole lump comes out of the nucleus. That's one kind of decay. Actually, there's another kind that is not part of the standard classification, which is the nucleus just loses a neutron. But so alpha decay is one type. Beta decay, which was the thing that was being asked about, here's what beta decay is. Beta decay, let's see how best to explain it. Basically what happens is a neutron is transformed into a proton, an electron, and an antineutrino. So protons, so far as we know, if you just take a proton, which is the nucleus of the standard kind of hydrogen, it's just a single proton. So far as we know, protons are completely stable. They were created, a proton that was created at the beginning of the universe, unless something hit it very hard, it's still around today, and it hasn't decayed and self-destructed in any way. And about in around 1980 or so, people had reasons to think, based on theories about particle physics, that the proton was likely to somehow be unstable. And so big efforts were made to try and find out if protons were unstable. How do you find out if protons were unstable? Basically, you get a great big tank of stuff, and you try and see whether any of that stuff spontaneously self-destructs, even though it was made of atoms that did not have radioactivity. It's a tricky thing to figure out, because how do you make sure there's absolutely no atom that has any radioactivity there? How do you make sure that there's nothing coming from the outside, like a cosmic ray of like a high energy proton coming from the sun or something, that kind of goes through your big tank of stuff? And so people typically put these big tanks of stuff in deep mines, a couple of miles underground, so that there's a couple of miles of rock sort of shielding it from anything coming from cosmic rays or something. And sometimes a popular place was things like road tunnels, and for example, Mont Blanc in the Alps, there's a road tunnel which is sort of drilled underneath the rock of Mont Blanc, and I guess there's a side room from the tunnel which is full of physics experiments now. But the next issue is, can you make sure that there's no kind of natural radioactivity in your tank of stuff? Because in the Earth, for example, it's pretty common to find radon, for example. It's a thing people worry about in houses and things like that, from different kinds of building practices and so on. But radon is a radioactive is radioactive nucleus that is quite commonly found and has a long enough lifetime that it sticks around for many years. I don't remember what the lifetime of radon is, maybe decades, a century, something like that. So it can stick around for that period of time. But so you have to make sure you don't have those kinds of things. You've got a lump you've got a big vat of stuff that is, as far as you know, just contains completely stable nuclei and potentially like hydrogen nuclei and water and things like this. And so far as you know, it's just going to stay there for the rest of eternity. And so what you look for is that proton that said, okay, time's up, I'm going to self-destruct. And what does a proton self-destruct into if a proton is going to self-destruct? It kind of has to be something that has a positive electric charge, and the only thing lighter than a proton that has a positive electric charge is an anti-electron or a positron. And so the decay of a proton would have to be into something like a positron, maybe neutrinos, which have almost zero mass, and maybe photons, which have zero mass. And so if a proton was going to decay, it would have to decay in something like a positron, neutrino, photon, things like this. And when that happens, that positron, because of the mass of the proton has to be converted into energy of that means that positron ends up being a rapidly moving positron, and you can observe sort of a rapidly moving positron because of the signature it makes in something like water. Well, particularly it makes a thing called Cherenkov radiation, because basically it's moving. Well, let me not particularly explain how that works, but it makes essentially a flash of blue light as a result of being this thing that's moving really quickly through a medium like water. So, okay, so as far as we know, protons are stable. Neutrons, on the other hand, are not stable. And if you were able to just get a free neutron, you were able to pluck a neutron out from a nucleus, the neutron will decay, and its lifetime is around 15 minutes. And what does it decay into? A neutron decays into a proton, an electron, and an antineutrino. And so a free neutron undergoes beta decay. A free neutron undergoes this kind of decay where you get out electrons and antineutrinos. And so what's happening in beta decay is that the neutrons that are in a nucleus, usually the nucleus is kind of holding the neutrons and keeping essentially the energy that's binding the nucleus together is making the neutron not be able to undergo that kind of decay. But somehow the neutron in a nucleus which is unstable to beta decay, the neutron is kind of loose enough that it's able to do what it would do if it was a free neutron and decay into a proton and an electron and an antineutrino. The reason that the neutron is not decaying in an ordinary nucleus in which doesn't have beta decay, essentially it's this: it's that there's a nucleus is held together by being bound together by all these protons and neutrons are stuck together by this thing called the strong nuclear force, which you can see in a variety of kinds of ways, but it's usually thought of as being due to the exchange of these particles called pions. It's a short-range force. It's unlike if you were to say how much it kind of makes all these particles stick together. But if you say, well, it makes something further away stick together, the answer is no. It has a range that is only about the size of a nucleus. So unless it's kind of just this very local thing. Now, in some cases, like in a neutron star is a giant collection of neutrons about 10 kilometers across. It's like a single giant atomic nucleus 10 kilometers across. It's the end state of stars a bit more massive than the sun. In a neutron star is held together by the strong nuclear force, where in a sense, every individual piece of the neutron star is kind of held onto the neighboring piece of the neutron star. And then altogether, you end up getting this, actually I guess the neutron star is ultimately held together by gravitational forces, but there's a local nuclear force that holds together individual pieces of the neutron star. In any case, so what happens in, how to explain this? The physics, the official kind of graduate school physics version of this is very straightforward, but let me see if I can explain it. Basic point is that in order for the neutron to decay, it has to be able to, so when a neutron decays, the mass of the neutron is being converted to mass and energy. There's a conservation of energy, which can either be in the form of mass or it can be in the form of sort of more traditional energy. And kind of the famous formula E equals mc squared tells you the conversion between sort of ordinary kinds of energy and energy associated with mass. And what ends up happening is that in if the neutron is kind of bound into a nucleus, it's the energy associated with that binding means that the sort of total energy of the neutron is made lower, and the total energy is sufficiently low that it is below the place where you would need, below the energy that you would need to account for the mass of a proton plus the mass of an electron. So the effective, normally, a neutron is slightly more massive than a proton, and that's why a free neutron can decay to a proton or electron. It has, the neutron mass is, what is it, 939 million electron volts, whereas the mass of the proton is around 938 million electron volts, and the mass of an electron is around 500,000 electron volts. And so the mass of a proton plus the mass of an electron is less than the mass of a neutron, which is why a free neutron can decay into a proton or electron. But when it's bound into a nucleus, the binding energy in the nucleus is larger than that difference, or can be larger than that difference. And when it's larger than that difference, the neutron simply doesn't have enough energy to be able to produce, to be able to make the mass of a proton and the mass of an electron, so it can't decay. And so that's why neutrons in most nuclei don't decay, but if the neutron is sort of a bit loose in the nucleus, it can decay, and that's what leads to beta decay. You can ask more questions about what is the underlying force, underlying mechanism for beta decay. I think I've talked about that previous time in connection with the standard model of particle physics. There's kind of these different kinds of forces that we know exist between particles. There's electromagnetic forces that are associated with electricity and magnetism, and charged particles, particles with electric charge, have those kinds of forces. Those forces are the result of exchange of photons. There are also the forces in nuclei, which I sort of explained are due to the exchange of pions, but there's well, again, it's a little bit complicated, but protons and neutrons themselves are composite particles made of quarks, and those quarks are held together by these things called gluons, which are kind of a little bit like photons, except that instead of dealing with electric charge, they deal with this thing called color charge, which is something that quarks have. And gluons have all sorts of weird properties. They, unlike photons, which only interact with charged particles, gluons have charge themselves. Photons don't have charge themselves. They only interact with other particles that have charge. But gluons have charge themselves, and so they have color charge themselves, so they interact with themselves, and that leads to all kinds of complicated effects. And it's sort of the fact that they're kind of interacting with themselves is what forces them to kind of remain localized and not be able to be seen as kind of free particles that you could just pick up and have a gluon detector or something. Roughly the whole mechanism of pion exchange, pions are quark, anti-quark particles, but it's all kind of connected to the way that quarks and gluons interact. So there's this strong nuclear force that's more or less, that holds nuclei together, that's more or less associated with quarks and particularly gluons. So there's this one additional piece where it's like, why does this exist? Well, we don't really know why it exists yet. But this is the so-called weak nuclear force, which is responsible for beta decay. And the weak nuclear force is associated with another kind of charge that is well, it's not usually given a specific name. It's an SU2 charge in the theory of in the standard theory of particle physics. But it's it's kind of another kind of charge, and instead of photons being the thing that is kind of is associated with that charge, are the things called W particles, and photons are massless. And if you have a photon, it will just if you shine a beam of light out into a vacuum, the beam of light will just keep going forever. Actually, that's not probably the best. The best, well, gosh, this is kind of complicated. You see, this is the problem that I always, in terms of sort of official graduate school physics, there's a fairly straight path through explaining what I'm trying to explain, but it's not so easy if you don't assume a whole bunch of knowledge about how physics works. But anyway, there's these things called W particles. And while photons are massless and travel at the speed of light and so on, W particles are not massless. W particles have a mass of about 65 times the mass of the proton. So they're kind of comparable in mass to a kind of a mid-range nucleus, a bit heavier than iron. Nucleus of iron, the most common version of the iron nucleus, has a mass of about 56 times the mass of the proton. But so the W particle is a bit more massive than that. It's just a single particle. And that W particle, it's the exchange of W particles that leads to weak nuclear forces or weak interactions. And it's those weak interactions that lead to beta decay. So a bit of a long explanation. But you can ask again, why do those weak interactions exist? We don't really know yet. We know that in a kind of a theory of and kind of the fundamental theory of physics as it's known in the standard model of particle physics, the sort of official words are, it's an SU3 cross SU2 cross U1 gauge theory. What does that mean? Those designations, SU3 and SU2, those are symmetry groups. Okay, what is a symmetry group? I can try and explain some of that. So imagine you have an object. Could pick up an object from somewhere here. Imagine you have an object and you can say, let's rotate that object around in space. We can ask the question, if we make a rotation, if we rotate it along one axis, we twist it around along one axis, then we twist it around along another axis, then we twist it around on the first axis again, and then we twist it around on the other axis. How do these different transformations combine? Is it the case that, for example, if we twist it around one axis by 90 degrees, then we twist it by another 90 degrees, and then we do that, let's say it's twisting around one axis by 90 degrees 4 times, it'll get back to where it started from. And we can keep doing these transformations, and we can kind of catalog what the combinations of these transformations do. If you think about things like Rubik's cubes, they have all kinds of transformations. And when you combine those transformations together, eventually you can get the Rubik's cube to go back to where it started from again. But there's this whole question of how do you catalog the possible transformations that you can make on things like cubes or like hexagons drawn in a plane or any of these kinds of things. You can sort of catalog those transformations. And there are things like rotations, reflections, all kinds of other sorts of transformations you can make. So you label each kind of transformation, and then you ask, what are the combinations of those transformations? How do they work? And that idea of sort of labeling transformations and seeing how their combinations work, that idea is all connected with group theory, which is a kind of a generalization of kind of the ideas of algebra in mathematics. It was invented in the 1830s. Originally by a chap called Évariste Galois. The idea is, if you think about something that says rotate 90 degrees, you can call that like R, for example. You do it again, it's like you've got R times R. Do it again, R times R times R. Do it yet again, R to the power 4. And if R represents a rotation through 90 degrees, for example, you could say R to the power 4 is equal to 1, because if you do the rotation 4 times, you get back to what you started from again, and that's like multiplying by 1. So it's like that gives you a relation in the group. You're saying you've got this transformation, this R, and you say that thing has a particular sort of algebraic relation, like R to the 4th is equal to 1. Or you might have some 2 different transformations. You might have a reflection here and a rotation there. And it might be the case that applying the reflection first followed by the rotation is the same as applying the rotation first followed by the reflection. That would be another kind of algebraic relation between those kind of symbolic things that represent those transformations. Okay, so group theory is this theory that you get by making up all these sort of algebraic relations between these transformations and then asking about different properties of the system that results. So for example, in a finite group, which means a group where there are only a limited number of these different elementary operations, elementary symbols in effect, a finite group, there'll be results like the fact that every element eventually has an order. So if you apply the element enough times, you'll eventually get back what you started from. And there are all kinds of other things about subgroups, pieces of the group where different elements in the group, different transformations, which can transform among themselves, but sort of stay away from other kinds of things. So for example, reflections rotations, for example, can be a separate subgroup that are independent of reflections. You can just think about the rotations on their own without ever getting involved with reflections and so on. So there are a bunch of results about group theory, and group theory is important in, well, lots of different kinds of things. It's kind of a way of representing symmetries of objects. And you can say, this object has this kind of symmetry. It has the symmetry of the square, for example, in the sense that you can rotate it around, and after you've rotated it 4 times, it comes back to what it started from. Or it has the symmetry of the icosahedron. So that's a 3-dimensional figure, and that means that all the transformations correspond to ones which are things like rotations, which take the icosahedron to itself. They're just rotations that just exchange faces of the icosahedron, so to speak. Okay, so that's sort of the idea of finite groups. And there are many sort of statements you can make about these finite groups, about orders of elements, about the way subgroups work, about different kinds of things. When you study crystals, for example, the atoms in crystals are arranged in definite ways that correspond to different finite symmetry groups. So, for example, if you have a crystal where all the atoms are arranged cubically, like in the case of sodium chloride, common salt, the atoms there are all arranged just in a cubic lattice. So there's like a big grid of that is just a big sort of cubic grid of like you just have cubical boxes and you're stacking them up, and it's like the atoms live in these cubical boxes and you're stacking them all up. But you can have other different kinds of crystal structures. For example, another common one is called hexagonal close packing. And for example, if you go to a grocery store, people still do that. If you look at the way that spherical fruit is packed, so for example, I don't know, something like oranges, you'll often see there'll be a big pile of oranges. And if you look at how those oranges are arranged, they'll be arranged in a way where there'll be sort of 3 oranges and then 1 orange on top of those 3 and so on. And that's a form of packing. That's a sort of closest packing. It's known, it was only proved very recently actually, that the closest packing of spheres that you could possibly get is the one that people have been using to stack fruit for centuries, so to speak. But that's also the kind of arrangement of atoms that exists in lots of kinds of crystals. And that kind of arrangement of atoms has a different symmetry group that has a, let's see, it's a dodecahedral symmetry group. No, that's not right. What is it? I'm not completely sure. Takes a bit of thought. It corresponds to one of the platonic solids, maybe the octahedron. The icosahedron, dodecahedron are kind of weird with respect to the symmetries like that, because they don't correspond to packings in the same way. Possibly liquids may have symmetry groups that are on average a bit like that. But anyway, so that corresponds to another kind of symmetry that's represented by one of these finite groups. Okay, so that's finite groups. Now, there's another kind of group, which is a continuous group, or Lie group, L-I-E, group named after a chap called Sophus Lie, who was Norwegian. The idea of a Lie group or a continuous group is it's dealing not with discrete transformations like rotate by 90 degrees and be back to the same after you did it 4 times, for example, but continuous transformations that can be arbitrarily small. So if you take a sphere, for example, or even a circle, let's just take a circle, if you move that circle just infinitesimally, you can just by an infinitesimal angle, that's an element of the continuous group of the circle. And you can just keep moving the circle infinitesimally. And if you do it enough times, eventually the circle will come back to what it started from again. But so what happens is there's a theory of these kinds of continuous groups. And it's a theory, it's kind of like if you know about calculus, calculus is a theory of continuous functions where it's sort of as if a function f of x, you change x just a tiny bit, the value of the function f of x will change just a tiny bit as well. Calculus is a theory of those kinds of sort of continuous changes. The theory of continuous groups is a theory of kind of continuous changes of continuous transformations associated with symmetries and so on. And so, for example, the group associated with a circle consists of, so it can be sort of generated by this infinitesimal transformation that you just turn the circle a little tiny bit. For a sphere, it's a little bit more complicated. If you imagine what are the infinitesimal transformations that you can make on a sphere, which if you did them enough times would let you turn the sphere from any configuration to any other, there's no longer just one kind of infinitesimal transformation, because you can kind of rotate the sphere on its sort of polar axis. You can rotate the sphere on its on sort of the around some point on the equator. You can make several different transformations. So there are several so-called infinitesimal generators of the symmetry group of the sphere. So in the case of a circle, the infinitesimal generators are just these things that just move you, turn the circle a little tiny bit. There's just one of them. On a sphere, there are 3 infinitesimal generators that are necessary to be able to, if you combine them and apply them enough times, you can turn the sphere from any sphere to any other sphere, so to speak. Just like when we're talking about a square, we're talking about transformations which take the square, rotate it through 90 degrees, which means you get the square back again. The same, you've made it the same square again, but just transformed. Same thing for a sphere, but now you're applying sort of an infinite number of these infinitesimal transformations. Okay, so you can index these infinitesimal, you can think about the sort of catalog of these infinitesimal transformations, just as you can think about the catalog of finite transformations for something like a square. And these infinitesimal transformations in the official language of kind of graduate school math are called the Lie algebra. They're kind of the sort of the infinitesimal piece of the Lie group, which corresponds to the set of all possible transformations of a sphere. So in any case, you can classify for different kinds of objects like spheres, the group of the sphere is called SO3, the special orthogonal group in 3 dimensions. And that represents, it has as its infinitesimal generators these 3 different transformations that you can make on a sphere, and you can have different choices of those generators, and it's all a bit complicated, but basically that's the idea. So for a sphere, SO3. For a circle, it's called U1. It could be called SO2 as well, but it's usually called U1. Is the kind of the Lie group that corresponds to transformations of a circle. And there are other kinds of Lie groups, but there's only a finite number of possible Lie groups. There are some families of Lie groups, like SO goes from SO, SO, any number. Actually, the ones in even numbers are different from the ones in odd numbers, but let's ignore that. But there are these differently labeled kinds of groups. There's another family of groups, the SU groups, SU2, SU3, SU4, etc. These are groups, mathematically, those are groups that can be represented using unitary matrices, but that's irrelevant for these purposes. They're just groups of symmetries of things that aren't quite geometrical objects like spheres. You can think of them, if you think about complex numbers, they're a version of kind of symmetries of things you can make with complex numbers, but you can just think of them as abstract symmetry transformations. Okay, why am I telling you all this stuff? Well, when we have sort of the physical objects in space, there are physical transformations you can make, like the things I was describing in the rotation group for a sphere. But one of the things that happens in physics is there is the notion of kind of an internal symmetry group, not something that is associated with space, not something that's associated with ordinary transformations of moving things in space, but something which is somehow associated with an internal space that exists in particles and so on. Now, actually, in our model of physics, there is a deep entangling of physical space of the kind that you can move around in, and this kind of internal space. And it's a quite elaborate kind of way in which the stuff that makes up physical space also makes up this kind of internal space. But roughly what's happening is that particles, there's this sort of internal space associated with particles, and you can think of it as, the particle is it's not like physically rotating around the particle. It's something that is an internal feature of the particle that is transforming in the kind of way that one would transform, for example, turning a sphere around. Okay, so that's a long story, but it turns out that those internal symmetries are, in physics, the internal symmetries associated with particles we know are, there's an SU3 symmetry, which is associated with the color charge. There's an SU2 and a U1 symmetry. Those are associated roughly with the weak charge and with electromagnetic charge. And okay, there's one more wrinkle here, which is this idea of so-called local gauge theories. Oh boy, let's see if I can explain this. So one thing you can ask is, you say, I have a sphere, I rotate it around, I want it to be the case that sort of nothing really changes if I just rotate things around. So let me give you an example of the universe, for example. Let's say that we have set ourselves up and we say we're setting up coordinates in the universe, and we say, the X direction in the universe goes from here to the Andromeda galaxy. The Y coordinate is going in the direction of some other galaxy or something. We've set up those coordinates, and we say, how does the universe work with respect to those coordinates? Then we say, okay, now I'm going to ask, is the universe rotationally symmetric? Does it matter whether one is? Does it matter to the laws of physics? Does it matter to the laws of mechanics whether this rocket is going towards the moon or towards Mars? Does it make any difference what the sort of actual orientation in space is for something? And the answer is, of course, if there are things in space like planets and so on, there can be gravity from those, and that makes a difference. But if you're just sort of in empty space, we believe that the universe is such that it is isotropic in the sense that it doesn't matter. Nothing depends on which absolute direction you're going in space. And so we can think about that as it is rotationally invariant. If we take the direction our rocket is going in and we rotate things around, we'll always get the same kind of physics for what's happening. Okay, so that's kind of at the level of large-scale physical space. Okay, when it comes to these internal symmetries, there is a somewhat different thing. Instead of saying we're just going to take the whole universe and rotate it around, we're going to say we can actually pick quite locally whether we consider sort of the X direction to be this direction and the Y direction to be that direction, or whether we can consider, we can treat it to be the case that completely locally we can pick which direction is X, which direction is Y, and so on with respect to this internal symmetry. And the claim that's being made is that physics is such that you can independently locally pick those coordinate systems. Now, if you just were to say, I'm just going to pick these local coordinate systems at random, so to speak, and then I'm going to pick them again, that won't work. What has to happen is if you pick them randomly at first, and then you say, oh, this one, I want to change this one, somehow, in order to make things consistent, the information that you changed this one has to be somehow propagated to other ones. And in the language of fancy mathematics, one talks about the symmetry group being associated with, one talks about the thing called the fiber bundle. And essentially what happens there is that there's sort of you think about at every point in space, there's like a fiber, like like a tuft in a carpet or something. If that was a two-dimensional space, it would be like the tufts in the carpet, and every one of those tufts is a fiber. And in that fiber, one's thinking about the operation of the symmetry group. It's a little bit hard to visualize but that's sort of the mathematical idea. Is there's this bundle of fibers. In every fiber, there's kind of a copy of the symmetry group, and every fiber you could sort of pick the coordinate system in that symmetry for that symmetry group separately. And then there's this notion of what's called a connection on the fiber bundle, which is kind of a mathematical concept at first that basically says if you move from one fiber to another, how does the coordinate system change from one fiber to another? You say, well, okay, that just sounds like a bunch of fancy mathematics. What does that have to do with anything real? It turns out the connections and fiber bundles correspond precisely to the idea of things like photons in electromagnetism. Because what's happening is electromagnetism is what's called a local gauge theory. It's a U1 local gauge theory. So in all of its sort of fibers, there's a copy of this U1 symmetry group, which is kind of the circle, the symmetry group of the circle. And what's happening is that sort of the orientation of those internal circles can be arbitrary, is different in different places in space. But sort of knowing about changes in that orientation, that the knowledge of that change is kind of carried by these photons that can go from one part of space to another. So that's kind of a very rough explanation of the idea of local gauge theories, which is the kind of the foundation of the sort of standard model of particle physics. And these particles, like the photon is said to be the gauge boson associated with the local gauge group for electromagnetism. The local gauge group for electromagnetism is U1. By the way, if you know more about how electromagnetism works, one of the things you may know is that you talk about, you have let's say, a circuit, and you say, there's a certain voltage between this part of the circuit and this other part of the circuit. There's a certain voltage across this resistor or something in the circuit. But the voltage, the voltage is a difference between electric potential. And electric potential is this kind of abstract thing that sort of defines the flow of electrons. When the electrons will flow from well, they're negatively charged, so it's all a bit messed up, but roughly they'll flow from higher electric potential to lower electric potential. But the zero of electric potential is not defined. You can say, this is my 0 volt place in my circuit, it's here, and then this other thing is plus 10 volts relative to the 0. Or you can pick the 0, put the 0 in a different place. You could say, actually, my whole circuit is, it starts off, my ground is minus 20 volts, and everything's relative to that. So it only the relative voltage matters, because that's what eventually is going to determine sort of the pushing of electrons through wires and things like this. And so that arbitrariness of the 0 voltage turns out to be the thing that is the local gauge, the gauge invariance associated with electromagnetism. What starts as being just this linear scale ends up being actually a rotation because of the way that one sets it up in terms of complex numbers and things like this. But that's kind of why that's a kind of a sign of this local gauge invariance for electromagnetism. But gauge invariance for electromagnetism leads to the existence of photons. Photons are sort of what carry the information associated with that. So for the weak symmetry, weak charges, the gauge bosons associated with weak charges are W particles and also Z particles. The gauge bosons associated with color charges are the gluons. And so there's kind of a very uniform way in which these theories work. It's a little bit weird, and it took a long time for people to understand this. Photons are massless. W particles, as I say, have a mass 65 times the mass of the proton. So how come one gauge boson is massless, another gauge boson has a great big mass? The thing that accounts for that is this thing called the Higgs mechanism, which is a kind of hokey piece of particle physics, which maybe will change eventually. But basically what happens is, really, the W boson sort of really is a massless particle, just like the photon. But throughout the universe, there's this kind of, there's this Higgs field that sort of permeates the whole universe. And as W bosons go through this Higgs field, they keep on getting stopped and started. They're interacting with this Higgs field. And that interaction causes them to behave as if they have a mass. And the Higgs field is actually the way that all particles are thought to get masses. But there are actually there are Higgs particles, which are kind of excitations in this Higgs field, and the Higgs particles themselves get mass from interacting with this background Higgs field. The Higgs particle has a mass of about 125 times the mass of a proton. It was only fairly recently discovered a few years ago in particle collisions and so on. So, okay, that was a very long explanation. I'm sorry, that was a let's see. There's a sort of follow-on question from this about from Lurch. Confused about the mass of quarks inside protons and neutrons. Yes. Okay. All right. In my compressed version of graduate school mathematical physics, let me try and explain that. So, inside a proton, roughly, protons are made of 3 quarks, 2 up quarks and a down quark. You can say, what's the mass of a proton? Okay, I can figure out the mass of a proton. It's 938 point something million electron volts. That's the measure of mass. It's about 10 to the minus 26 kilograms, if I remember correctly. So it's a very there's a definite mass for a proton. So you say, well, what's the mass of an up quark? I'd have to say, well, I don't really know. Say, how can you not know what the mass of an up quark is? After all, every proton in the universe has a couple of up quarks and down quark in it. Well, the reason is that quarks never exist outside of things like protons and neutrons, so far as we know, and probably the case. The quarks are permanently confined inside protons and neutrons. What happens if you kick a proton really hard? Let's say you fire an electron into a proton and it kind of kicks the things that are inside the proton. Well, what happens is the proton will kind of deform and it'll, kind of a piece of it will be push out to one side. But it turns out that the forces associated with gluons are such that the further you pull it out, the stronger the force will be. So, for example, if you have a spring, you pull a spring, the more you pull the spring out, the stronger the spring will try and pull you back. If you have something which has a gravitational force or an electromagnetic force, the further apart those objects become, the smaller the force will be. It goes down like the inverse, the 1 over the square of the distance in that case. But if you have the force associated with color charge, the force associated with gluons, that force is one that actually increases as you pull the things further and further apart. It increases probably roughly linearly. If you pull the thing apart, it'll just get, this force will get stronger and stronger. So that's kind of the reason why there aren't any free quarks, because if you try and pull the quark out, it will pull it a certain distance. Actually, what will happen is if you pull it far enough out, there will be so much energy associated with the pulling back of that quark. There will be enough energy to create quark-antiquark pairs from the vacuum. So in other words, there will be so much energy there that it is, there'll be enough energy available that they can make masses of quarks, that energy can be used to make a whole quark and to provide the mass necessary to make a quark. So you can ask, why is it the case that these gluons and things produce this force law that's so different from the force law associated with other gauge bosons like the photon? The reason is because gluons interact with themselves. Photons do not. Photons, if you take 2 beams of light and you shine them through each other, they'll just go straight through. There's a tiny effect called light by light scattering where photons will actually interact with each other, but it's a tiny, tiny, tiny effect. And it has to do with producing virtual electron-positron pairs and all kinds of fancy quantum field theory things. But it's a very small effect. For gluons, if you could make beams of gluons, which you can't because they're permanently confined inside things like protons, but if you could make a beam of gluons, you took these 2 beams of gluons and you had them collide, they would just interact. They would dramatically interact with each other. They wouldn't just go straight through each other. Okay, so what does that mean? Well, it means if you imagine gluons you have 2 quarks here and here, and you have the forces between these quarks are associated with essentially gluons being produced, bouncing back and forth between these two quarks. The question is, as these gluons, normally, if you have something like an electric charge, it's effectively producing what are called virtual photons, all streaming out in all directions. And the photons don't interact with each other. So a photon that's streaming out along, from the North Pole doesn't interact with the one that's streaming out from the South Pole, and so on. And so as you get further away from the thing where these photons are all streaming out, at any given place, the density of those photons will be smaller and smaller, because they're streaming out in all directions. And so you can see that the number that hit any particular region will get less and less as you get further and further away. However, in the case of gluons, the gluons interact with each other. So instead of it being the case that the gluons can also stream out in all directions independently, the gluons all gum themselves together. And effectively what happens is the gluons make this kind of string of gluons between particles, because the gluons, instead of wanting to go out all separately in all different directions, the gluons want to all be together. They want to all make this sort of single lump of stuff. It isn't really a lump. It's all much more virtualized than that. But that's kind of the idea. They all kind of clump together. And so that means there's this kind of string of gluons between particles. And that means as you pull the particles further apart, instead of it just being the case that fewer and fewer gluons can hit the other particle because they're further away and they're sort of streaming out in all directions, the same number of gluons get to the other particle, and so the force doesn't go down. So that's roughly the reason for the fact that the force associated with gluons goes up with distance rather than going down with distance. But that's the reason that gluons are sort of permanently confined, that quarks and gluons are permanently confined inside particles. And when they're permanently confined, that the other thing that happens is that sort of confinement has, just like nuclei have a certain binding energy associated with the fact that the neutrons and protons are all being sort of pulled together. The same is true inside protons. There's a certain binding energy, and actually the majority of the mass of a proton is just binding energy. So in a nucleus, most of the energy of a nucleus is most of the mass of a nucleus is accounted for by just adding up the masses of the protons and neutrons inside it. There's a small mass defect typically associated with the binding energy that holds the nucleus together. But that mass defect is usually maybe 1,000th of the mass of the nucleus, something like that. Mass defect is very important, and changes in that mass defect are what allow you to have nuclear reactors and what lead to radioactive decay and all kinds of things like this. But it's a small effect relative to the mass of a nucleus. In the case of a proton, the vast majority of the mass of a proton is associated with gluon binding energy that holds those those particles together. The thing that so when you have something like a proton, the up and down quarks have very low mass, and so that binding energy is important. When there are 6 kinds of quarks that we know about. Probably that's all that there are. The up quark, the down quark, those are in protons. The strange quark, the charm quark, the bottom quark, and the top quark. Top quark was only discovered fairly recently, has a mass of 173 times the mass of a proton, roughly. If you have a particle made from top quarks and bottom quarks, charm quarks, things like that, in that case, the binding energy is actually quite small compared to the mass of the quarks. The binding energy is usually roughly, well, it's on the order of maybe 1/10 the mass of a proton, something like that is kind of the binding energy. In your average, well, it's a little bit complicated, but in your average proton, the binding energy is about the mass of the proton. In the pion, which is about 1/10 the mass of a proton, there's binding energy there, which is slightly smaller for various reasons. But basically, in these light particles like protons, light relative to other things like protons, most of their mass is contributed by binding energy. When you get these things made with heavy quarks, there's an amount of binding energy that's comparable to the mass of a proton, but that's small compared to the masses of these quarks. So that was boy, that was a long description of lots of particle physics. Let's see. Well, there's all kinds of questions here. Let me just address a couple more. So a question here. Do you think you'll be able to wirelessly charge your house in your lifetime? Depends on how much you want to be cooked. I mean, when you have these wireless chargers, how do they work? They are inductive chargers. So one feature of electromagnetism is that if you have an electric current going around in a circle, in a wire, then it will tend to induce an electric current in another wire. And that's how these inductive charges work. It's the process. I mean, it's a little bit more complicated than that and involves magnetism, but that's roughly the idea. And what's happening is that there is it's an electromagnetic, it's not an electromagnetic wave like light. It's another way in which electromagnetism, in which one piece of electric activity can affect another piece of electric activity. It's the same underlying equations, the same underlying theory, but it just is applied in a slightly different way than it is in the case of producing something like a light wave or something of that kind. But electromagnetic induction is the way these charges work is by using electromagnetic induction. But I think it's the case that if you want to, and there's sort of, that produces an electromagnetic effect that can go through space like an electromagnetic wave, like a photon, like a light or something, but it just has a different characteristic. And I think I backed myself into. I can explain how that works, but it requires a bit of fancy discussion, I think, about the details of how electromagnetism is set up. But suffice it to say, that process of sort of transmitting electromagnetic energy from one thing to another, that energy exists between those things. It's kind of like the same kind of energy that exists inside a microwave oven or something. It's sort of it's an electromagnetic field that exists in sort of an empty space, so to speak. Well, the problem is that electromagnetic field has an effect on charged particles like electrons that exist in the things that it encounters, and that's why it has the effect of being able to charge your phone or whatever. It's sort of moving around the electrons, and just like plugging the phone into the wall would be pushing electrons around that eventually will charge the battery of the phone. So if you have that kind of electromagnetic field and you're trying to charge things that way, the problem is that if you have something that's in that electromagnetic field that isn't the thing you're trying to charge, like if you walk through that electromagnetic field, then you will be charged, so to speak, or more to the point, you'll be treated kind of like food in a microwave oven. You'll have kind of electromagnetic, you'll have the same kind of electromagnetic processes that cause the molecules in the food in a microwave oven to spin around and heat up and so on. Those things will happen to you. And I don't know whether there's a way to avoid that happening. I would suspect, there's sort of the question of whether there's a way to have inductive charging so that you don't have something that can also cook other things. And I don't know the answer to that. People believe a magnetic field, a pure magnetic field that doesn't um, a magnetic field like the one you get from a bar magnet, for example, people might think that that has no real effect on us humans. You know, you have a bar magnet, you put it next to your hand, doesn't seem to do anything to your hand. We don't seem to have any magnetic. Nothing about us seems to care about magnetism, about ordinary static magnetism, not electromagnetic fields, which involve changes of electrical and magnetic potentials and things, but just static magnetic fields. We don't seem to care about those. Well, more or less. People have long believed that, for example, pigeons are sensitive to the magnetic field of the Earth, that somehow there is inside one of the proteins in the brain of a pigeon, there is something that in which the way that the spins of electrons are aligned is affected by the Earth's magnetic field, and that the way the protein operates depends on these electron spins, which in turn are affected by the Earth's magnetic field. And so people have believed that sort of homing pigeons partly home by virtue of knowing the direction of the magnetic field. And so a recent but fairly credible theory is that there are actually many proteins that are sensitive to magnetic fields. And for example, it could very well be that the proteins that are associated with our circadian rhythm, our kind of the way that our bodies change when we get used to sort of a roughly 24-hour cycle of light and dark, sleep and wakefulness and so on. There are proteins that are associated with that kind of clock, that rhythm. And there's some evidence that those proteins actually are affected by magnetic fields. So the idea that there's nothing in us that cares about magnetic fields may not, in fact, be true. Whether we should worry about that and whether we should be thinking about, gosh, if we live in this big magnetic field, is it going to change us in weird ways? I don't know. It certainly always used to be said by physicists I knew who worked around very large magnetic fields that you could have, you know, if you were in a high magnetic field, you get this strange taste in your mouth. And it's not completely implausible why that might happen, because there are features of kind of the way that the electrochemistry of taste works that might depend on some magnetic kinds of processes. And of course, then the question is, if you get, you know, an MRI done, which involves a large magnetic field, you know, does that happen? And one doesn't usually hear about that. So that's probably a sign that there isn't such an effect there, but I'm not sure. But so I think the answer is it's for things necessary to do charging. I don't think that, I think that's tough to make it work. There's a comment here from Anders. Didn't Tesla invent wireless electricity? I don't know exactly what Tesla invented along those lines. I think it was this kind of inductive charging idea, but I'm not sure. And William is commenting, does solar count as wireless charging? I don't know in some sense, but that's a little weird. I mean, in solar power, what you're doing is you're taking light and using photovoltaic materials, which just mean turning light to electricity, materials to generate electricity. And what's basically happening is a photon from the light hits essentially an electron in the material and kind of makes it be, gives it energy that essentially generates an electric voltage that is the thing that is what can be used to charge a battery or generate power or whatever else. So essentially, instead of you having a voltage that is which you get sort of from the outside and pulling electrons through that way, essentially what's happening is that photons are giving electrons the kick that they need to generate a voltage, and that's sort of the rough way that photovoltaic cells work, and they work well, in more detail, they work using semiconductors, the same kind of thing that's used to make microprocessors and so on, but set up in a different way. Well, I think we should probably wrap up soon. I'm sorry, I've spent longer than I expected on that physics question. Yeah, somebody is commenting that Tesla's wireless power experiment, the Wardenclyffe Tower. Now, that thing is in New Jersey, and I think it's in New Jersey at least. Pretty sure I've seen that thing. It's in some. I think there's a big effort to make a museum around it, and I don't know whether that's been successful yet. But I think it's in New Jersey, and I think I've seen the thing, and it's sort of just in some random parking lot, and it's kind of nearby Thomas Edison's sort of much fancier workshop. Not sure. Okay, maybe one more question, maybe a simple one. Let's see if there are any simple ones here. Oh boy. Well, okay, I'll do two here. There's one from Anna. Can human electromagnetic fields interfere with electricity? So us humans have definite electrical effects of different kinds. So for example, the way that, well, we are in a first approximation sort of bags of water, and our cells contain lots of water. That's the most common substance in us, and water has certain electrical properties. And so when we have, well, here's a very elementary case. So when you hold a cell phone, you are, actually, I'm not sure how this works these days. If you hold the metal part of a cell phone, you are definitely becoming part of the antenna for the cell phone. If you have a case on your cell phone, I'm less clear how that works actually. But if you hold the sort of let's say old-fashioned thing, if you have sort of one of those antennas that's just kind of a straight kind of telescoping antenna or something made of metal, and you grab onto that antenna, you in a sense become part of that antenna. And so the electromagnetic waves that antenna is picking up, it will potentially pick up more of those electromagnetic waves by virtue of you act as some piece of the sort of antenna that's connected to that. Now, the way that works with cell phones is kind of complicated, because one of the issues is when you pick up a cell phone, the cell phone usually will try and decrease its power, the amount of power it's sending, because it's trying to not cook your hand, so to speak. And so there's all kinds of different things. If you look at for example, the filings that are made with the FCC, the Federal Communications Commission, by companies like Apple, they show all the tests that get done on things like cell phones to show, how much electromagnetic radiation are you getting in your hand and so on. And I think there are these different kinds of grips that you can make to a cell phone. I think there's one that gets called maybe it's called the Vulcan death grip or something, I'm not sure, but it's one where you're really holding on very, very tight. And the phone will react to that and change the amount of energy that it's putting out into its antenna. And it has a very elaborate kind of system of trying to have the phone put up as much energy as you can. I think maybe not sure whether the phone these days sort of uses you as part of its antenna or not, and then trying to sort of not cook you, so to speak. But in general, humans have a big effect on electromagnetic waves that are sort of propagating around. Like if you have Wi-Fi, Wi-Fi is electromagnetic waves that are propagating around, and you can, if you measure in detail the amount of the Wi-Fi signal collected at different places, you can detect the fact that people are walking around in a room by just seeing that the Wi-Fi signal will be attenuated by somebody walking in front of something, et cetera, et cetera, et cetera. So you can have an effect that way. When it comes to our nerves, for example, work electrically. We're generating electrical impulses. That's what our nerves use to drive our muscles. If you're asking whether it's possible for that kind of electricity to have an effect outside, I don't think so for humans. If you're an electric eel, it's a different story. An electric eel kind of produces its electricity in the same kind of way. It's kind of like a battery, same way that electricity is produced in nerve cells and so on. But the electric eel is kind of a, does it as a sort of oversized nerve cell. And the electric eel produces enough charge, it gets itself charged up enough that it can actually have an effect and, attack its prey using by giving it an electric shock and so on. I don't think humans can do that. I don't think we have any mechanism for generating enough electric charge to be able to do anything like that. Although, one could imagine some strange story where somebody has managed to train themselves to operate their nerves and muscles in just such a way as to be like a kind of simulation electric eel, but I haven't heard of such a thing. So that's the story there. All right, last question for today from Cast. What is something you've recently changed your perspective or opinion about? Maybe this is too long gosh. That could be too long a question. I mean, one example of that, this is going to get me into a way long answer, which I can't really give right now. But the question of consciousness and what consciousness is something that I have always avoided because I've always thought there isn't anything very scientific to say about it. And I realized a little while ago that actually with our new theory of physics and so on, there is a way to think about kind of what consciousness is and the way in which consciousness kind of sort of defining feature of consciousness is something that one might have thought was sort of a triviality and not the main point, but is actually a defining feature. And it's the notion that there is a definite kind of sequence of experience that consciousness corresponds to. In other words, we have a definite sort of thread of experience. That's an essence of sort of our conscious experiences. There's a definite thread through time of experience. It's not like all these different things are happening, all these different places, and all the different neurons in our brains are firing and doing different kinds of things. Rather, sort of an essential feature of consciousness is at least this perception that there's a definite kind of sequentialized thread of experience that kind of runs through what we experience and remember and so on. And what I've kind of realized is that sort of notion of a sequentialized thread of experience is something which deeply affects the way that we view the world. And if it wasn't for that, we would view things like space and time and lots of other kinds of things in very different ways. The fact that we have this kind of sequentialized view of a definite thread of experience is ultimately what drives the way that we perceive the way that the physical world works. And so that's something I've very much changed my mind on. If you'd asked me 6 months ago what I thought about consciousness, I would have said, I don't have anything to say about it. I now think there's something very definite to say about it. And it all has to do with this kind of sequentialized thread of experience, which is what leads us to the physics that we have. If we didn't have that sort of sequentialized thread of experience, we would have a very different view of how the universe works and what physics is like. And so that's led me to all kinds of interesting thoughts about whether consciousness is sort of what you would conclude about the universe if you were set up differently, and kind of how you would parse the different pieces of space and so on in the universe if it wasn't for the fact that you have this sort of sequentialized thread of consciousness. Also makes me realize that things like human language, which is a very sequential thing, it's one word comes after another, comes after another. We don't have sort of an array of different things going on. We tend to think about things in sort of a sequential fashion like that. We tend to express them in language in a sequential fashion. That seems to me to be, I'm realizing, not something which is just, it happens that way and we could train ourselves to do something different, but that's a fundamental feature of the way that we exist and the way that we experience the world. And that has consequences if you're trying to program a computer and you want the computer to be doing all sorts of different things, all roughly at the same time in parallel. That's a thing that has been very hard for people to understand how to do. And I think we're kind of seeing why, because in some sense, it's something that is incompatible with our core features of consciousness, so to speak. And so that's sort of the reason for that difficulty. And it kind of gives one some idea of how one might try to resolve that difficulty, or maybe it's really hard because us humans are just stuck in this kind of thread of experience way of thinking about things. We can imagine the AIs, and we can imagine sort of they might have a different way of doing this process of thinking about things. The problem is, if they don't have something which is sort of sequentialized like our thread of experience, they will just look to us as if they're doing kind of random computational things, just like any old system in nature. They won't seem to have the same kinds of thinking like processes that we have. So this is something that I've rather changed my mind on, and to make a bit of a cliffhanger, I think one of the things that that view of things has led me to is back to a really old question, which is one of these questions which it's like, how could you possibly answer this question? Which is, why does the universe exist? And put a different way, why is there something rather than nothing? Why does anything exist? And the surprise to me in the last, week or two is that I actually think I've got now a credible answer to that question, which depends deeply on kind of a stack of ideas that come out of sort of studying the computational universe physics project and so on. But it's kind of interesting. And I've been sort of surprised as I've been looking around at, what do other people say about why does the universe exist? And why is there something rather than nothing? And I have to say it's pretty thin. There's a lot of kind of wordplay about, well, if there's nothing, then you can't talk about it, so therefore there has to be something and so on, but that's really just wordplay. And in terms of having any kind of reasoned account of that, it is surprisingly thin from what I have found. And it's been really a surprise to me that I think there is a sort of scientific kind of answer to that question, and hopefully coming in the next few weeks. We'll see. And but it's one of those things where it's a pretty elaborate sort of tower of logic, although in the end the argument is fairly simple. And if it wasn't fairly simple, I really wouldn't believe in it at all. But that's something that, as I say, I would have said if you'd asked me. Well, I've been sort of thinking about this a bit for the last year, because once one has what one thinks is a fundamental theory of physics, a fundamental theory of the universe, the obvious question is, why this universe and not another? Why, and then why is there any universe at all? And I almost feel a bit silly, and RJ here has commented that I should give the sum up here is, quotes, I've answered why there's something rather than nothing, tune in next week. And I suppose I could say that, but I almost feel a bit silly even having a discussion of that question, because it seems like one of these questions that's just fraught with sort of philosophical wordplay and so on. But as I say, to my surprise, you asked me the question, what's something I've recently changed my perspective or opinion about? That's something I've changed my opinion about, and how that's going to work out, we will have to see. Maybe I'll change my opinion again and realize that what I figured out so far isn't right for some reason, but it looks pretty solid to me. Okay, I should wrap up here for now, and thanks for joining us, and see you another time.